Okay, so there are some exceptions to the octet rule. So the octet rule, right, is in order to have a stable valence shell, you need 8 electrons, 8 valence electrons. But there are some cases where the central atom can actually have more than 8 or less than 8 and still be stable. So it's just one of those you kind of have to remember. So boron and beryllium, they're actually really, really small atoms. And so, they actually are okay without having 8. So boron sometimes will only have 6 valence electrons, and then beryllium sometimes will only have 4. And so that's kind of how it works for those. So you'll see, and just don't be alarmed by it. Just know that boron and beryllium sometimes they have less than 8. Atoms in period 3 or greater actually have the possibility of having more than 8 valence electrons. And because remember, in period 3 you have the s, the p, but you also have these empty d orbitals that are available. And because of these unfilled d orbitals, they can actually expand their octet. And so sometimes you'll just see that they have a little extra. So if you have a central atom and it has greater than it's in period 3 or greater, it is possible that it could have more than 8 valence electrons. Let's do some examples. This first one is BCl3. So B has 3 valence electrons. And then this is, let me pause it for a second. And then chlorine has 7. So the total number of valence electrons is 21 plus 3, which is 24 electrons. So we have 24 electrons to work with. Boron is our central atom. So you got chlorine, chlorine, and chlorine. I have used up the bonds. I've used up 6, right? 2, 4, 6. So this will give me 18. I'm just going to go ahead and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, at this point, you might think like, boron only has 2, 4, 6. And so you might do this. You might be like, well, let me throw an extra so that boron can have a double bond, so it can have 8 for the octet, right? But actually, the most stable form is actually like this. And the reason is because boron, having 6 is fine with boron, okay? So that's one of the exceptions. Here's another exception, PCl5, phosphorus pentachloride. So let's do the math real quick. So phosphorus has 5 valence electrons, chlorine has 7. So that's going to be 40, right? So 5 plus 35 is 40. All right, so let's go ahead and do it. So immediately you kind of know that there's going to be, this is kind of one of the exceptions because you have 5 chlorines and they all are bonded to, so you kind of have to make space for them, I guess. So I 1, 2, 3, 4, 5. So I used up 10. So that gives me 30. So here's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. That's it. So I used up all 30. And so it happens that phosphorus actually has 10 valence electrons in this particular configuration. Okay? All right. Let's look at another one. This one's a weird one. So xenon. Xenon's a noble gas, but because it's so big, sometimes those outer electrons it doesn't really hold on to as well, and so they kind of participate in bonding. So xenon has 8. It's kind of this one of these exceptions. Fluorine has 2, so 7 times 2 is 14. So 14 and 8 is 22, right? So Xenon is bonded to fluorine. That gives you 18, 2, 4, 6, 8, 10, 12. So I use up 12, which is 6. So 2, 4, 6, 8, 10, 12, 14, 16, right? So that leaves me 6 electrons that I have to put on Xenon. So Xenon disobeys the octet rule. It's kind of a weird one, but that's what happens. So remember, what you do is, if you remember the steps, we put the bonding electrons in first, right, and then we fill the terminal atoms, and then anything remaining we just throw on the central atom. Okay. And this one happens to disobey the octet rule. SF6. So sulfur is 6, fluorine is 7. There's 6 of them, so that's going to be 48, right? 42 plus 6. All right, so let's check this out. So fluorine's going to bond 6 times to sulfur. There's 4, 5, and 6. And so 2, 4, 6, 8, 10. That's 10, right? That's used up. So now I have 38. Now go ahead and put them on your terminal. So that's 6, right? 12, 18, 24. Oops, put too many. 30. All right, so we used up 36, right? We have 6. So, oh, I'm sorry. You know what? I did something wrong. So this should be 12, right? Sorry. So this would be 36 because there's a 1, 2, 3, 4, 5, 6. There's 6. So 6 times 2 is 12, and so this should be 0. Let's look at SF4. So S is 6. F is 4 times 7. So this would be 28 plus 6 is 34. Four are bonded to fluorine. So you get 8, 26. So 2, 4, 6, 8, 10, 12. 14, 16, 18, 20, 22, 24. There's 2 remaining, so we got to put the extra 2 on sulfur. Okay? All right, so we'll stop here. The next one will be on polyatomic ions.